Another one. Show that E sub x on the axis of a ring charge of radius A has its maximum and minimum values at x equal to A over square root of 2 and negative A over square root of 2. Sketch EX versus x for both positive and negative x values. What this means is you have a ring charge like this, and we are talking about electric field at a point on the axis of that. Do you remember that equation? Well, the electric field at a point on the axis of a ring charge is kqx over a squared plus x squared to the power of 3 over 2. I think I got that right. Can you check back? Where A is the radius of the ring, x is the distance of the point from the center, is that right? And q is the amount of charge on the ring. Now, we are told to show that at x equal to A over square root 2, there will be a maximum or there will be a minimum. In other words, you can see as you go away from the center of the ring, what do you think is the electric field at the center of the ring? You see, at the center the electric field will be 0 because each segment on the top will produce a field at the center opposite to the field produced by the segment opposite to it. So the field will be 0 there. And as you move away, the electric field will increase. It will reach a maximum somewhere, and thereafter it will reduce. Also, as you go to the left, the field will be 0. It will be negative, directed to the left. It will be a negative minimum and then become 0 almost. So we would expect that the electric field will increase to the right, reaches the maximum, and then decrease to 0. On the left, 0 decrease to a minimum and then go towards 0. That's what we would expect. Is that right? Okay. Ex for a ring that carries a charge Q is given by Ex equal to kqx over x squared plus a squared to the power of 3 over 2. See, that's the only thing you need to know to solve this problem. And now, where Ex is maximum, the derivative of this will be 0. E prime x will be 0. Can you find the derivative of this? Well, you need to use the quotient rule. Well, it will be, what's the quotient rule? Can I remind you? It will be denominator multiplied by derivative of the numerator minus the numerator multiplied by derivative of the denominator all over the square of the denominator. Well, that would be a challenge for some of you to do that. So e prime x, I have done that for you. Look at this. The denominator, to the denominator, multiplied by derivative of kqx with respect to x will be kq. The derivative of 5x with respect to x is 5. The derivative of kqx with respect to x is kq. The denominator multiplied by derivative of the numerator minus numerator kqx times the derivative of the denominator. Denominator is a power. The derivative is the power multiplied by the quantity x squared plus a squared to the power of n minus 1. 3 over 2 minus 1 is 1/2 times the derivative of the quantity there is 2x. All over the square of the denominator is x squared plus a squared to the power of 3. Let's simplify this. How do we simplify it? Now look at the way I simplified it. I took out kq times x squared plus a squared to the power of 1/2. Can you understand that? X squared plus a squared to the power of 1/2. When you take it out from here, from a 3/2, when a 1/2 comes out, there is 1 left. That means what is left here is x squared plus a squared minus what is left there. First of all, if you notice, I cancel those 2, so that 2's don't exist. Now you can see kq times x squared plus a squared to the power of 1/2 has come out. What is left here is x squared plus a squared minus what is left here will be 3x times x squared. And simplify that, you get kq times a squared, this x squared plus a squared to the power of 1/2 cancels with x squared plus a squared to the power on the denominator. Can you see that? That will leave x squared plus a squared to the power of 5/2 on the denominator. I hope you follow my simplification. That leaves on the numerator kq times a squared minus 2x squared minus 3x squared is minus 2x squared. Now this is the derivative of that quantity. When the quantity Ex is a maximum or a minimum, that derivative will be 0. So let's set that equal to 0. When this becomes 0, now do you know that a rational expression becomes 0 when its numerator is 0? You see that? So when this quantity is 0, when you set this quantity equal to 0, what will be 0 will be this, the numerator will be 0. And when the numerator becomes 0, you see kq cannot be 0. Therefore, what will be 0? A squared minus 2x squared will be 0. That's right. The quantity e prime x will become 0 only when this a squared minus 2x squared equal to 0. So we take that quantity and set it equal to 0. That will be, remove the 2x squared to the right side, it will become positive 2x squared equal to a squared, or x squared equal to a squared over 2, or x equal to plus or minus a over square root 2. That's right, that's what we have been told to show. So the electric field has a maximum value or a minimum value at x equal to plus or minus square root 2, and look at the plot of that. You can see the electric field is 0, as we were talking about in the beginning. The electric field is 0 at the center. As you go away from the center, the field increases to a maximum, and this distance is a over square root 2. And on the other side, you have the minimum. So x equal to a over square root 2 is this, where you have the maximum, and x equal to negative a over square root 2, you have the minimum value. Done enough problems, and using Gauss's law is an important part of static electricity. And in the next lesson, we are actually going to use Gauss's law to obtain some of these familiar equations that we use calculus to do. Alright, I will see you for that lesson later on. In the meantime, do all your homework and make sure you feel comfortable with the theoretical interpretations of this part of the course. Okay?